Hello, chemistry people. Amy here. What I've got for us today is the revision lecture on equilibrium, which is topic 7. This is an SL revision lecture. So for HL equilibrium, you're going to have to see the videos that I'll be making in a week or so's time. Any questions, anything like that, please do let me know in the comments. Just giving you a heads up, I am in the process of migrating all of my videos to a new account. I will be putting out a video to let you all know where those are later on. I am changing jobs, which means that my current YouTube channel, which is linked to my current school, needs to be migrated. Okay, thank you so much, and let's get started. Okay, so let's get started. So this is topic 7. As always, we start with the study guide. So I'm basically going to be going through all of these guys. I might need to do a little note on the side about KC relationships, but definitely going to do the rest of these guys, really focusing on the Chateliers because that's where a lot of the questions come up on exams. So equilibrium, in the IB, we talk about homogeneous. Equilibrium, that is where, so homo means same. So in a homogeneous equilibrium, everything is the same state. So whether you've got a whole bunch of liquids or a whole bunch of aqueuses or a whole bunch of gases, we don't tend to talk about solids in equilibrium. So when we say equilibrium, we are talking about a process. So a chemical reaction where, so let's just say I've got A plus B reacting to form C and D. Now, so far in all of the chemical reactions we've spoken about, we've used a simple arrow. That means that 100% of the time, A plus B reacts to form C plus D. Now, I'm going to have to pause my recording because I've had a Year 7 wander into the Zoom. Give me just a second. Okay, so in previous years, you might have been told that one of the differences between chemical reactions and physical changes is that we can't reverse chemical reactions. The entire topic of equilibrium is all about those reactions that go both backwards and forwards. So in my container, I have both A and B reacting to form C and D, but also C and D are reacting to form A and B. Now, for a reaction to be at equilibrium, it has the same macroscopic qualities. So my solution remains the same color, or it remains the same amount of substances, but the individual atoms that make up A and B are constantly reacting to form C and D, and vice versa. Okay, so for something to be at equilibrium, the rate of the forward reaction has to be equal to the rate of the back reaction. Now, at equilibrium, we talk about a closed system. So I can't be adding or removing stuff at equilibrium. I need to retain those initial points. Okay. So the equilibrium law is a mathematical relationship between the different products and reactants. So in general, in a chemical reaction, I have reactants that react to form products, and products that react to form reactants. So how we would express the equilibrium constant for that, we do the concentration of products over the concentration of reactants. That's in general. Let's do this for an actual reaction. So one of the classics that we always use for this is the formation of ammonia. So I'm going to do 2NH3 gas is formed by N2 gas and 3H2 gas. Oh, sorry, really important point. This is concentration. We have to be dealing in concentration. Think about the role that concentration played when we were looking at rates of reaction. That is how this is linked. We have to be talking about the concentrations of our products and reactants because it's concentration that has an effect on reaction rate, not amount. So the equilibrium law for this is product. So it's going to be concentration of NH3 divided by concentration of N2 and concentration of H2. The important thing, and it's something that despite the fact that you've got chemistry teachers like me screaming about it, a lot of the time students forget to put the powers on. So whatever the mole ratio is, you put it as the power on that concentration. So let's look at a related reaction to this one we've just seen. So what if instead of forming 2 moles of NH3, I only want to form 1 mole of NH3? That means I would only need half a mole of nitrogen and 3 on 2 moles of hydrogen. The Kc for this would be NH3 to its power, which is just 1, then divided by my reactants. So that is going to be N2 to the power of 1/2 times hydrogen concentration of to the power of 3 on 2. So can you please look at my green Kc? So I'm going to call that Kc1 and this blue Kc2. What is the difference between these 2 mathematical expressions? So I'm going to switch off blue because that would be confusing. Let's go with purplish pink. So as I'm going from Kc1 to Kc2, I'm basically taking the square root of it or taking it to the power of 1/2. That's because I halved the mole ratios. Okay. Let's now look at yet another related equation, and I'll go with the paler blue. So what if I am in fact breaking down 2 moles of ammonia gas and turning it into 1 mole of nitrogen gas and 3 moles, 3 moles of hydrogen gas. Kc3 would be concentration of H2 to the power of 3 times the concentration of nitrogen divided by concentration of ammonia squared. So what is, again, let's go back to our first equation. Let's compare Kc1 to Kc3. What is the relationship between Kc1 to Kc3? It's the inverse. And that is because I have reversed that equation. This type of question is very popular on multiple choice. What is the relationship between the Kc values of these? So they give you the Kc of a particular equilibrium, and they say, what is the Kc for this equation? And it will be either halved, so you either halve your mole ratios or double your mole ratios, or it's the inverse reaction. It's actually one of the simpler ones to do. So equilibrium law takes us really neatly to equilibrium constant. So the equilibrium law in general. So I start with reactants and it reacts to form products. My equilibrium constant is the concentration of products over my concentration of reactants. Okay. So the equilibrium constant is where I take this equilibrium expression and I substitute numbers into it. So if you are given the concentrations of hydrogen, nitrogen, and ammonia at equilibrium, I can chuck those numbers in and get a numerical answer. So just logically, if I have a reaction where I have a lot more products than reactants, this Kc is going to be very much larger than 1. That means that depending on the reaction, we can almost show that arrow as just a forward arrow. If I have a reaction where my reactants are very much, sorry, I'll write them the same way. So if I have a reaction where I have a lot more reactant left than I have with product, my Kc is going to be very much less than 1, which means that my reaction, instead of being 2 arrows like this, it's like this and that. So the back reaction is very much favoured. This is something we talk about in HL quite a lot. If my products are roughly equal to my reactants, my Kc is roughly going to be equal to 1, which is where we get that sort of true equilibrium. We won't necessarily have exactly equal mole amounts of products and reactants, but we end up with appreciable amounts of both reactants and products in the mix at equilibrium. So with the equilibrium constant, once you've worked out a number for your forward reaction, you should be able to apply any of these transformations to work out the Kc of a related reaction, just by either to the power of half or squaring everything or taking the inverse. Okay, I am going to pause for a moment. I've just had another year 7 show up. Excuse me a sec. Okay, where were we? So we've just talked about equilibrium constant and the role of the magnitude of the equilibrium constant. Let's move on and talk about Le Chatelier's principle. So Le Chatelier's principle, the way I always teach it to my classes, and part of me doesn't mind whether it's accurate or not. I always start with, because there's almost always somebody who speaks some degree of French in my classes, I always ask them to tell me what le chat means. And it's about cats, because cats are lazy. So just like cats are lazy, my chemical systems are lazy. If you disturb them, they want to go right back to doing what they were doing before. So Le Chatelier's principle is about, and let me just pause for a tick so I can get exact wording on this from a textbook. So if a system is at equilibrium and we make a change to that system, the equilibrium will shift to minimize the effect of the change. So it's about minimizing change. So let's go back to our A, B, C, D. So whenever I change my equilibrium, whenever I make a change, so let's say I react away all of my A, I take out my A, my equilibrium will shift in order to replace it. It is all about minimizing change. The other way you will sometimes see this worded, and it depends on what other curricula your chemistry teacher teaches, partial So another way you will hear Le Chatelier's expressed is if a change is introduced to a system, the equilibrium will shift to partially oppose that change. Okay. So let's look at some of these changes. So let's change pressure and let's go back to our, let's look at methanol. So if I've got carbon monoxide gas and I react it with 2 hydrogen gas molecules, it equilibrium forms CH3OH gas. So if I'm changing pressure, I have to be talking about gases. So let's talk about what happens. So my forward reaction has 1 mole of gas, and on my reactant side, I have 3 moles of gas. So let me demonstrate to you why I nearly failed art in high school. If I have this reaction going on inside a container that looks like this, and then suddenly I change the volume of my container. Now, you guys remember gas laws enough to know that by decreasing pressure, I've increased, sorry, by decreasing volume, I've increased pressure. So How does my system, remember those key words, partially oppose or minimize the effect of that change? My system minimizes that change by favoring the side of my equation that has fewer moles of gas. So when you are asked this question on an exam, the key point is mentioning that it is of gas or of gaseous reactants or products, making sure you talk about it being moles of gas or a change in the number of gas molecules. In order to partially oppose the increase in pressure, my equilibrium shifts. So it is favouring the side of the reaction that has fewer moles of gas. Now, one thing that is super important, so I'm going to put it in big red letters, there is no change to equilibrium constant. No change. If I measure the concentrations of my guys in this container and put them into my equilibrium expression, the number will be exactly the same as it is in this container. I am going to talk about it more later. The only thing that changes equilibrium constant is temperature. It's an equilibrium constant. It's constant because it stays the same most of the time. So changing pressure is what we can do to gases, and it is all about what number of, how many moles of gas do I have on either side. If I've got the same number of moles of gas on both sides of my equation, there's no real effect. It will increase the rate of the reaction because my molecules will be colliding more often, but the equilibrium itself won't change. So what I might do, if I remember how to do this, and I'm just going to put a big note for myself so I can see it. I'm going to see if I can add a column here, because I have an experiment where I made some NO2 gas and put it in a syringe so I could actually change my volume. So if you're interested, check that out, because it is a practical view of changing pressure and Le Chatelier's principle. Changing concentration is pretty much for aqueouses. So changing pressure was for gases, changing concentrations is for aqueouses. So let's talk about CO, and I'm not going to do the complex ion. So these are both aqueouses, sorry. And this is in equilibrium, and COCl4 overall 2 minus. Okay, so this thing here is a really pretty pinkish color. And this guy over here is actually like a purpley blue. This equilibrium is often used in water detecting strips, because if you dry it out and you turn it into that purpley blue form on a piece of paper, you can then put it on, put it into a mixture to see if you've got the water out. Because if there's water, it'll go to this pinkish color. So let's change my concentration by adding a whole bunch more and Cl minus. If I do that, if I increase my concentration, remember, partially oppose. So my equilibrium will shift to partially oppose that change before we reach our new equilibrium. So if I increase my amount of chloride, my equilibrium will shift before I reach a new equilibrium. When I reach that new equilibrium, my amount of CO2 plus will decrease, my amount of Cls will decrease, and my amount of COCl4s will increase. So I have my initial, then it changes, then I'm at an equilibrium. There is a specific reason I've done that. And again, that's what we talk about at HL. So when I'm monitoring the changes in concentration, one of the reasons why I've specifically talked about the colours of these things, oh, sorry, I've just slipped. One thing that will change is the colour of this solution. So if I am consuming that pinkish cobalt species and making more of this purplish blue, I will end up with a solution that is more purplish blue than it was initially. Again, I will add a card here, hopefully, where I have a series of Le Chatelier's experiments looking at, I want to say it is the copper ion rather than the cobalt, but changing various factors and seeing how it affects the position of equilibrium. So adding or removing a product or reactant, this should be getting pretty straightforward at this point. So let's go back to A, B, C, D. So think about that ice table I drew before. If I initially add a whole bunch more C, the change will be against that addition. And then at equilibrium, my C and D will have decreased and my B and A will have increased. Initial, then I change, then it's equilibrium. The opposite goes if I remove something. So let's say I remove some A, that's my initial. My change opposes. So my equilibrium, I restore my A, I gain a little bit of B in the bargain, but I consume C and D to make that happen. Now, with all of these guys here, there is no change to Kc. So if there's no temp change, there is going to be no change to Kc. Sorry. This is one of those simple things that kids, when they're stressed and they're doing an exam, they see constant and they see my concentrations changing before they get back into equilibrium. And they talk about the equilibrium constant changing. It is one of those things that is consistently asked for 1 mark on an exam, and consistently kids mix it up. If you are changing anything other than temperature, I don't have a change to Kc. Let's talk about catalysts. Okay, so what do catalysts do? So catalysts, remember our definition, increase the rate of reaction by putting an alternate pathway. Oh, be good if I could spell. Pathway with lower activation energy. So catalysts increase the reaction rate by generating an alternate pathway with lower activation energy. They increase the reaction rate by doing this process for both forward and back reactions. And here is where you gain or lose the mark equally. So a catalyst increases the rate of reaction by creating an alternate pathway with lower activation energy, and it increases both the forward and back reactions to the same extent. Does it equally? Okay, let's now talk about changing the temperature. And changing the temperature depends on whether you're dealing with an exo or an endothermic reaction. So let's start by looking at an exo. So if I have 2NO2 gas in a container with N2O4, the delta H on this side is negative, so it's an exo. The way I introduce this is think about energy as being a product or reactant. So if this is exothermic, energy is a product in this reaction. So now we can think about it just like we thought about adding or removing a product. If I increase the temperature, so initial change equilibrium, if I increase the temperature, I'm adding energy. So my change is going to be to use up that energy so that at my new equilibrium, that's what's happened. So let's relate this to actual numbers for the magnitude of that equilibrium constant. So my Kc initial, let's just do that. My Kc initially here is, let's just call it prod on react. So once my temperature has increased, so I'm going to call that Kc hot because I'm obvious like that. So do I have decreased my amount of product and increased my amount of reactant? So my Kc, when it's at a higher temperature, is going to be smaller than the Kc initial. Let's look at what happens if, for this reaction, I reduce the temperature. So initially, I am going to reduce my energy, which means that my change, my partial opposition, is the reaction moves forward so that at equilibrium, I have less NO2, more N2O4, and more energy. My Kc initial is the same, but my Kc when it's cold is going to be greater than it was initially because my concentration of my product has increased. The same logic applies in reverse for an endothermic reaction. Think about changing the temperature as adding or removing a product, but that product is energy. That reactant or product is energy. And this is the only thing that can change my equilibrium constant. Okay. One thing, sorry. I'm just going to pop this off to the side because it's something that isn't explicitly talked about in the curriculum, but I've seen it come up as a question a few times. There are a number of industrial processes where they are exothermic reactions. So, hang on. I think, excuse me a sec while I pause and find an exothermic reaction. Okay, so I did remember correctly. The Haber process, which is this guy that I've written about 3 times already today. This guy has a delta H of negative 93 kilojoules per mole. So the equilibrium would be favoured because it's exothermic. So in theory, if I make this a lower temperature, I will get a greater output of that ammonia that I'm trying to make. But that's slow. So what we will generally do in industry in order to keep that rate of reaction up, remember kinetics, what will often be done is they will keep the temperature high, but then use catalysts and have a process by which the ammonia is removed from the reaction vessel in order to keep driving that reaction forward. So even though having a lower temperature looks like it would be what would be done to make the most ammonia, it makes it really slow. So it's better to get 90% efficiency at going a lot faster than 100% efficiency going a lot slower. So that's what the chemical industry tends to do, and it's for kinetics reasons. That is a question I've seen come up once or twice. Okay, so let's talk about reaction quotient, and I think that's the end. Yes. So reaction quotient. So earlier we talked about equilibrium constant as being this fraction of concentration of products over the concentration of reactants. But let's say I've got a container. Let's stick with Haber process. I know we've talked about it like 30 odd times. And yes, I know that's an exaggeration from the last one I said. But let's talk about Haber process. I have a container of nitrogen and hydrogen that I've left on the bench for a while, but I'm not sure whether or not that is at equilibrium. So what I do, I take a sample of that and I measure the concentrations of each of these guys. And then I substitute those numbers into the Kc. So the Kc is for when it is at equilibrium. The exact same fraction, but with different numbers, is for when we're not sure whether it's at equilibrium or not. So the expression to use reaction quotient is the same. So this is going to be concentration of ammonia squared divided by concentration of nitrogen and concentration of hydrogen cubed. Remember, you always have a calculator for these guys. So I substitute in these values because I'm not sure whether or not I'm at equilibrium. And then, so if Q is equal to Kc, you are at equilibrium. If Q is less than Kc, what that means is that I don't have enough product. So the forward reaction, oh, sorry. So the forward reaction is going to be dominant. If my Q is greater than Kc, I have too much product, which means that my back reaction is going to be dominant. So reaction quotient is exactly the same fraction as we developed all the way back at the beginning of this topic. It's just the application for when I'm not sure whether I'm at equilibrium or not. Okay. Let's talk about our study guide. So equilibrium is in a closed system when the rates of the forward and reverse reactions are equal. The equilibrium law is the fraction that tells us how we can work out Kc. The magnitude of the equilibrium constant tells us the extent. The quotient is the equilibrium expression with non-equilibrium concentrations. And the position of the equilibrium changes with concentration, pressure, and temperature. And the catalyst has no effect on the position of equilibrium or the equilibrium constant because it affects both the forward and reverse reactions equally. Make sure you're writing the word equally or the IB get crabby at you, and as will I and your chemistry teacher in class. So chemical and physical systems at equilibrium, that's those macroscopic qualities. I've shown you how to get the equilibrium constant expression and relationship. So whether it's the inverse or the half or the squared, depending on how exactly I've shown that reaction. We've talked about Le Chatelier's. We've talked mostly about chemical systems. They very rarely ask about physical systems, but think about like a closed bottle of soda water where you've got CO2 gas and CO2 aqueous. That's the sort of idea. And we don't need any specific examples of any industrial processes. Odds are, if you are given a question on this, it's going to be ammonia, or it's going to be contact process, which is SO2 to SO3, which we talked about in acid deposition. Okay, that brings us to the end of this revision lecture. Thank you so much. Sorry for those interruptions from my year 7s. Have a fantastic rest of your day, and I shall see you next time. Bye.